Hello viewers. Today in these sessions, we are going to cover the topic named as differential flow meters. So it is one kind of the flow meters where we can able to measure the flow rate, but we are going to measure the flow rate by measuring the differential pressure. So the question is how we are going to measure the flow rate by measuring the differential pressure. So today we are going to answer that questions. So before to know that, first we have to know the continuity equations. So the continuity equation says that the overall flow rate of a system is constant throughout that system. That means if I take a systems like this, a pipe is there having the cross-sectional area of A, and a fluid is passing through that pipe having the flow rate Q with a velocity V. Then the flow rate, that is V into A, the velocity multiplied with the cross-sectional area, is remains constant throughout that system. This is known as the continuity equations. So the continuity equation is given as the VA is constant. Now what we can imply from that continuity equations, that if I able to change the cross-sectional area of that pipe, instantaneously the velocity of that same fluid is going to change. If I reduce the cross-sectional area, the velocity should be increasing in nature. So if the fluid is moving through a pipe having different cross-sectional area, whatever I am talking about, then the flow rate, that is the volumetric flow rate Q, is remains constant. So if I take this diagram number B, I have 2 points. This is the point number 1. This is the point number 2. And it is clearly observed from these sections. Then point number 1 having the cross-sectional area is A1, and point number 2 having the cross-sectional area is A2, and both are not same. A1 is higher than the A2. So as per the continuity equations, the flow rate should be constant throughout the system. So if I going to calculate the flow rate at point number 1 and the point number 2, that should be same. But due to the variation of the cross-sectional area, the velocity should be different. So as the area A1 at point number 1 having the higher value compared to the area at point number 2 is A2. So in terms of the velocity, the V2 should be the higher value compared to the V1 to validate the continuity equations. Similarly, if I am talking about the mass flow rate, what will be the picture? Then for the mass flow rate, the picture is like that. The ρ1 V1 A1 is equals to ρ2 V2 A2, because we know that if I going to multiply the density with the volumetric flow rate, we will get the mass flow rate. So the continuity equation is also true for the mass flow rate. So the flow rate is constant. So the whatever be the ρ1 V1 A1 at the point number 1 is remains constant in any point, and that is equals to ρ2 V2 and A2. So this is the first things we have to know about the differential flow meters. Apart from this continuity equation, one more thing we need to know, that is the Bernoulli's equations. What Bernoulli said? Bernoulli says that for an inclined and tapered tube, that thing is important. For an inclined and tapered tube, what does it implies? It have an inclinations, that is inclined tube. It's not a horizontal tube is there. It having a inclinations. So if it having the inclination, if I consider 2 points, here is a point number 1 and here is a point number 2, then we can clearly observe that the height of this point number 1 and point number 2 is different. And it is only possible if the pipe is inclined. If the pipe is a horizontal one, then H1 and H2 for point number 1 and point number 2 respectively is exactly equal. So that is the first point. the inclined tube, and the tapered tube. What does it mean by the tapered tube? Tapered tube means it does not have a uniform area throughout that pipe. So that means if I see this, observe this diagram, we can observe that the cross-sectional area is not constant within that tube or within that pipe. So to understand the Bernoulli's theorem or Bernoulli's equations, we have to consider such a tube which is inclined as well as tapered. So for such kind of system, Bernoulli says that the sum of pressure head, velocity head, and the elevation head is equals to constant. That means if I consider the 2 point number 1 and the point number 2, so in both the points, these three heads, the pressure head, velocity head, and the elevation is remains constant. Now, one thing we have to understand over here, we are talking about head. We are not talking about the pressure plus velocity. We are not talking about the summation of pressure, velocity, and elevations. We are talking about the pressure head, velocity head, and the elevation head. So what is the difference between the velocity head and the pressure head? So the difference is velocity head, the definition is the vertical distance through which a liquid would fall to attain a given velocity. Say we want to attain a velocity v1 or v. So what should be the vertical distance is required so that a liquid will attain the velocity v if it is in a stationary conditions. That means how much height is required to attain a liquid of the given velocity. The velocity may be anything, v, v1, v2, whatever it is. So we know the formula that v square equals to u square plus 2gh, where v is the final velocity, u is the initial velocity, and h is the height. So to attain the given velocity v, and initial velocity is 0. So if I put the 0, u is equal to 0, then we'll got the equation v square equals to 2gh. And we are talking about head, velocity head. We are not talking about the velocity itself. So head means that height. So the velocity head, the expression is v square divided by 2h. So that is the difference between the velocity and the velocity head. Velocity is v, but here the velocity head is the v square by 2g. Similarly, for the next part, for the pressure head, here also the difference is there in between the pressure and the pressure head. So what is the definition of the pressure head? The definition for the pressure head is the vertical distance which a common column of the flowing fluid would rise with an open end tube as a result of static pressure. That means if I apply that amount of pressure in a manometer, what should be the height difference of that manometric fluid is defined as the pressure head. So we know that from the principle of the manometer, the del P equals to rho gh. So what is del P? The final pressure minus initial pressure. So initial pressure is here 0. So we can write here del P is equals to P itself. So P equals to rho gh, and we are interested to find out the h value, that height difference, head value. So the pressure head is equals to P by rho g. So see, the pressure is P, but pressure head is P by rho g. And the third term is there, that is the elevation head, and that is nothing but the height difference of that point from the ground. Now, if I write down the expression for the Bernoulli's equations, it looks like P1 by rho g, the pressure head at point number 1, plus V1 square by 2g, the velocity head of the point number 1, plus H1 is the elevation head of the point number 1, is equals to P2 by rho g plus V2 square by 2g plus H2. So this is the equations of the Bernoulli's theorem. Now, if I just multiplied this rho g with this upper end, then the equation becomes P1 divided by rho V1 square by 2. It should not be G. Here a mistake is there. It should be 2 plus rho G H1 plus P2 plus rho V2 square by 2. It should be 2. It should not be G plus rho G H2. So this is the Bernoulli's equation we will get from the Bernoulli's theorem. And this is for a inclined and tapered tube. Now, what is the applications? How we are going to apply the Bernoulli's theorem and the continuity equations to measure the flow rate? The perfect example is the Venturi tube. If we observe the Venturi tube, it's a horizontal tube. So the first thing is it's not a inclined tube, it's a horizontal tube. But what we can observe here, that it having the cross-sectional area is different in different sections. Here it's a pipe diameter, here it's a minimum area diameter is there. Again, it will be increasing in nature. So the Venturi tube is simply the tube which is narrower in the middle than its ends. Now, what will happen whenever we are reducing the cross-sectional area? And that point, the continuity equation play the role. And for that, the velocity is going to be increasing in nature. So whenever the fluid passing through the tube reaches the narrow part, it speed up. Why it speed up? As per the continuity equation, because the cross-sectional area is less. So the velocity should be increasing in nature. And whenever the velocity is increasing in nature, then what is the velocity head? Is v square by 2g. So if the velocity is increasing in nature, so velocity head is also increasing in nature. And as per the Bernoulli's theorem, if the velocity head is increasing in nature, so the pressure head should be decreasing in nature. Because here the elevation is constant, it's a vertical tube, it's a horizontal tube. No inclination is there, the angle is 0. So if I take the elevation head over here at this point and elevation head over here at this point, both are same. So elevation head should be cancelled out in both the part. So if I use a Venturi tube like this kind of structure, then what will happen? Then as per the continuity equation, the velocity is going to be changed. And as per the Bernoulli's principle, the pressure is also going to be changed. And if I just rewrite the Bernoulli's theorem, then it should be like that: P1 plus rho V1 square by 2. It should not be G, it should be 2 plus equals to P2 plus rho V2 square by 2. It's again 2, right? Just a minute. It should be 2. So it should be 2 here and it should be 2 here also. Okay. So now that I already discussed, that from the continuity equations, what I have, that V1 A1 equals to V2 A2. Now, as the A1 is greater than A2, A1 is the point number 1. That means this point is the A1 and this point is the A2. So A1 is definitely higher than the A2. So definitely the V1 is less than V2. So if I put that thing, then if I rearrange these equations, we will get the equation is P2 minus P1 is equals to rho by 2 into V1 square minus V2 square. So the pressure in the narrower section will decrease as the velocity will increase. That will observe, that is for the Bernoulli's principle. So here from we'll get one thing, that if I made such an arrangement where the cross section is going to be changed, if I put some restrictions in the systems, then the continuity equation takes place. And if the continuity equation takes place, then the velocity is going to be changed. And if the velocity is going to be changed, the velocity head is also going to be changed. and then the Bernoulli's equation takes place and the pressure head is going to be changed. To see the consequences, I just put a restriction and so many things that happen, and at the end we will get a differential pressure. So if we could measure the differential pressure, I could or we could able to measure the flow rate of that systems. Now the question is, you can see this diagram, a picture is there, and the question is written over here, why you cannot stand near the train which is high in motions. All of we have that experience whenever we are visit any railway stations. Some announcement are like that, through train is passing through platform number, these passengers are requested to keep the safe distance. What is for that? Why we have to keep a safe distance from that? This is also an example of the Bernoulli's theorem. What happened? Whenever a high motion train is just passing in front of a persons, then the distance between that person and the train is very less. So the velocity, because the high speed train is there, so the velocity in between that portions, that means the persons and the train, is very fast compared to the backside of that persons. So if the velocity is high, pressure is low on that sections. So we can we will feel that an invisible hand just put up that persons towards that train. So an accident may happen. So this is the practical example of the Bernoulli's theorem, isn't it? So when we stand close to a train which has a high speed, the air that moves the trains has to pass from the channel saved by your body and the train. So the speed of the air has to increase to pass this narrow channel, definitely, because the restriction is less. Thus, the pressure of the air between you and the train falls dramatically. So now in this case, the motionless air behind your back have the more pressure, because in the front edge, the less pressure is there. So what we'll feel, that we feel that an invisible hand will push you towards the train. And what should be that force of that invisible hand? That will also depends on the train speed and the distance, the restrictions and the velocity. So we cannot stand close to a high speed train. So we have to be careful for that. Now come to that part, that what is the operating principle of the DP type flow meter. As I told that a DP type flow meter means it's a flow meters. We are going to measure the flow rate, but actually we are going to measure the differential pressure, and we are going to map the differential pressure in terms of the flow. How could we achieve this? Now, to understand these things, we require two knowledge, whatever we have already discussed. One is the continuity equations and another is the Bernoulli's theorem. Now consider these sections. We having a pipe or tube, and we'll make that tube structure is like this. We'll consider this point as a point number 1, say this one is point number 1 and this one is point number 2, say. What we can see that the area of this point is lower than this area of this point. That means the area of the point number 2 is less than point number 1. So at that moment, the continuity equation takes place and the velocity V2 at point number 2 will be higher than the velocity V1 at point number 1. If such kind of thing is happen, then the Bernoulli's theorem takes place and the pressure P2 at point number 2 having the lower value compared to the pressure P1 at the point number 1. So we'll just measuring these two pressure, the pressure P1 at point number 1 and pressure P2 at the point number 2. So we'll get the differential pressure. So as per the Bernoulli's theorem, P1 plus rho V1 square by 2, P2 plus rho V2 square by 2. Right? So now, as per the continuity equations, as per the continuity equation, what we know that Q is equals to V1 A1 minus equals to V2 A2 at the point number 1 and the point number 2. And also we have already derived this equation from the previous slide, but that from the Bernoulli's equations, we know that P2 minus P1 is equals to rho by 2 V1 V2 square minus V1 square. So if I replace the V1 value, because here from this continuity equations, we know that V1 is equals to nothing but V2 A2 divided by A1. So if I could replace this V1 value over here, then the equation becomes V2 square as a common into 1 minus A2 square minus A1 square divided by A1 square equals to this part is same 2 by rho into P2 minus P1. So we are interested to find out the velocity. So the V2 is nothing but 1 by under root of 1 minus A2 square divided by A1 square multiplied with under root of 2 by rho into P2 minus P1. We get this value. And this V2 is nothing but 1 by 1 minus beta to the power 4. We just replace this A2 square by A1 square as a beta to the power 4. And this one is 2 by rho P2 minus P1. That is the del P, we can say. P2 minus P1 is a del P. So this is known as the velocity of that fluid. So we can see here that velocity of that fluid we can able to find out, and that having the direct relations with the differential and pressure. How they are relate? They are proportional with the square root of the del P. So V is directly proportional to the square root of the differential pressure. Here a new term we have coined here, that is beta, that is d2 by d1 or under root of a2 by a1. So what is the definition of that? This is known as the beta ratio. The definition is the ratio between the diameter of the restriction and the diameter of the pipe. How the restriction is, what is the ratio is there, and that ratio is known as the beta ratio. And beta ratio is a very, very important parameter for all the differential pressure flow meters. Now we are interested to find out the volumetric flow rate. Still we are find out the velocity, that is V2, and we know the volumetric flow rate is nothing but the velocity is multiplied with the area. So the volumetric flow rate is nothing but A2 V2 is equals to what will happen, that the rest of the equation is as it is, just we are multiplying this A2 part. So from these expressions, what we can conclude that if there is any obstruction in the flow path, if there is any restriction in the flow path, then the cross-sectional area is going to be changed. And if there is any cross-sectional area is change is there, then as per the continuity equation, the velocity is going to be changed. If the velocity is going to be changed, then the velocity head is also going to be changed. And if the velocity head is going to be changed, then as per the Bernoulli's theorem, the pressure head is going to be changed. And if I measure this del P, the pressure head, change in pressure head, and we have a direct relationship with the volumetric flow rate, and that is nothing but under root of del P. So whatever the question is coined, that how by measuring the differential pressure we will measure the flow rate, that question is answered in this slide. But one limitation is there. This equation is valid for the incompressible fluid. If the fluid is compressible, we need more adjustment. So different types of the classifications are there. The common differential pressure type flow meters are orifice, venturi, and nozzle. We'll cover one by one later. These are the most commonly used the differential pressure type flow meters. And other are also there: segmental type, V-cone type, elbow type, dull tube type are there. And one more thing is there: always the differential pressure type of flow meter are used as secondary component, because the primary devices is just a restrictions, and due to that restrictions, the pressure difference is created. To measure the pressure difference, we need a pressure measurement devices, which is known as the secondary element for these flow meters. It may be anything. It may be manometer, starting from manometer to diaphragm, whatever it is. We'll also observe in later class that the differential pressure transmitters are there. They will use the diaphragm to measure the differential pressure. So always, whenever we are going to use the differential pressure flow meters, we need a secondary element to measure the pressure difference, because the primary element will convert the flow rate into differential pressure. So we need a secondary element which will measure that differential pressure, and from that measurement we can able to predict, or we can able to calculate what is the actual volumetric flow rate of that system. So this is the things. So in the next class we'll start about the orifice plate, and we'll go by one. So this much for today's sessions. Thank you very much.